Hi everybody and welcome to lecture 11 for Phil 2002, Logic, How to Defeat Your Foes with Reasoning. Today I'm joined by Starbuck the Unicorn. Starbuck, say hi. And we're going to be discussing the semantics for monadic predicate logic. So in the previous lecture, I introduced to you a new language, monadic predicate logic, which included a syntactic construction that has in it some extra elements for translating out new kinds of arguments. So some of the arguments that we were translating were arguments that involved these new kinds of features like the concept of everything or the concept of something, and also concepts like the property of being a certain thing or particular objects, so names for particular objects and things that are picked out by definite descriptions. So we have a syntax for the language, and the syntax is defined recursively, just as the syntax for propositional logic was defined recursively. We have a statement for what it is that constitutes a kind of basic proposition in the language. And a basic proposition in the language is a predicate letter followed by a name or a variable. So every predicate letter has got some slot following it in which you can drop a name or a variable. And then the basic propositions can be concatenated or combined using some of the propositional connectives to produce complex propositions. And then from there you can add quantifiers into those complex propositions to build quantified statements inside monadic predicate logic. And this gives us the ability to say more complex things than we had the ability to say in the previous language. So previously we couldn't say things like everyone is happy, or at least if we could say that, all we could do is translate that entire proposition out as a propositional letter. Now what we can do is sort of zoom in on the structure of that sentence by translating out the components of the sentence using things like all and some and the property of being happy. But so far, all we have is a syntax. So we just have a way of writing down these symbols, and we know the grammatical rules under which those symbols can be written, but we don't yet have an interpretation of the language. And what we're going to be trying to do today is provide an interpretation of the language. We're going to be interpreting these symbols so that we understand what they mean, and then once we've got an understanding of the meaning of those symbols, we can then turn to the topic of validity and invalidity, and then we can start to look at proof with respect to this kind of language. So in this lecture, I'm going to give you the semantics for monadic predicate logic, going to introduce that to you step by step, and then in the next session, I will connect this back to the concepts of validity and invalidity to prepare us for developing a new form of the truth tree system which will enable us to prove things about arguments. Okay, one of the key things to understand about the semantics for monadic predicate logic is that in a certain respect it is quite different to the semantics for propositional logic. So the semantics for propositional logic was in effect exhausted by the truth table system, and that was enough to get us all of the symbols that we needed and to interpret them adequately, and indeed enough to be able to prove things when it came to arguments. We could take an entire argument, situate it inside a truth table, and then carry out the proof, and everything worked well. When we're dealing with monadic predicate logic, however, the truth table system has a limited amount of usefulness. In a certain respect, the truth tables are still operating in the background. They're still there for our basic propositional connectives, which are carried over into monadic predicate logic. So we still sort of have the same conditions under which those things are true or false. However, what we also need is something more complex to handle these concepts like all and some, and these notions like the property of, and then things like names and so on. Ultimately, what we're going to be doing is working towards the production of a model. And a model is a sort of complex, abstract artifact which enables us to understand each of the components of this new language that we're dealing with. And later on, validity itself is going to be defined over these things that we call models. All right, so to get us started, what we need to do is we need to think about properties and predicates. The core to the semantics for monadic predicate logic is the predicates and properties that we've introduced that we then can put variables or names into. And what we need in order to understand these properties and predicates that we've introduced, so each predicate, remember, is just represented by a predicate letter, so things like PX or BX or AA, these capital letters with a slot following them, those are the predicates that we have in our language. And the core to the semantics for monadic predicate logic involves interpreting these things. So we're going to focus on interpreting these things. Once we've got an interpretation of these things, that will help us to produce an interpretation of the universal quantifier and the existential quantifier as well. Okay, so let's start with our concepts of property and predication that are represented by these capital letters inside monadic predicate logic. Okay, consider the following proposition in monadic predicate logic. PA, okay? Now that's just a piece of symbolism. I haven't told you what it means. So what I'm now going to do is I'm actually going to interpret this particular predicate. So what I'm going to say is that this predicate P corresponds to the property of being red, and A, the lowercase a, picks out a particular thing, namely the planet Mars, all right? So the PX predicate corresponds to the things that have the property being red, and A is the thing that we call Mars, right? So that's picking out the planet Mars. Now, if I say this to you under that interpretation, so I've given you a little bit of a meaning of the symbols, if I give you that meaning, you can understand whether or not this sentence that I've started with, this claim, just PA on its own, is true. How do we understand whether or not it's true? Well, we look to see if the thing that A picks out, namely the planet Mars, is in fact red, right? So that's the sort of core idea here. When we've got a predication like this, something like PA, we look to see if the thing that falls into the slot following the predicate does in fact have the property that the predicate is picking out. So if the predicate picks out the property is red, and the lowercase a in this case picks out the planet Mars, then in order to work out whether or not this is true, we look to see if Mars is in fact red. Right? It's a very simple idea, but what we need to do is we need to make that a little bit more general and a little bit more abstract, because when we're dealing with monadic predicate logic, we don't necessarily want to be talking about any particular planet or any particular property. Sometimes we want to be able to just talk about properties without specifying any particular one, and also we want the language to have a kind of flexibility to it so that we can substitute in different properties depending on what kind of argument that we're interested in. So we need to have something a little bit more general. And the more general thing is something that we're going to introduce in a moment, and it's the concept of an extension. Before we get there, however, what we need to do is we need to just have a little bit of a think about what it is for the planet Mars to be true. And when we say that, we need to think a little bit about what it is to say that the planet Mars is red, is true. We need to think a little bit about that, and what we can do is we can actually represent it visually. So here's just a visual representation of what it is to say that the planet Mars is red. So here we've got the property of being red, so that's the thing that's encapsulated by the red circle, and then inside that circle we've got all of the red things, right? So when we say that Mars is red, what we're actually saying is that with respect to the red things that there are in the universe, Mars is one of them, right? And that's really the core idea behind the extension of a predicate. The extension of a predicate corresponds to the set or group of things to which that predicate applies. So for instance, the predicate is red just corresponds to the set of red things. But different predicates are going to have different extensions. So consider the predicate O, X is orange. Right, so this predicate just specifies the set of orange things, and I can visualize this by just drawing a picture of all of the orange things in the universe. Of course, this is a very simplified picture. There's more in the universe than just the things that I'm drawing right now, but hopefully you get the idea, which is that the property of being orange just corresponds to the group of orange things. And so when we're talking about the extension of a predicate, we just mean this boundary here. The extension of the predicate just is the set of things that corresponds to the property that the predicate seems to pick out. So when OX corresponds to the property being orange, it picks out the orange things. Okay, so what we're going to do now is we're going to look at some different concepts of extension. We're going to look at different predicates that have different types of extension. We're going to look at some examples, and then we're going to apply this to the universal and existential quantifiers. First, however, it's very important to note that a predicate, like the property being red or some other property, can actually have an empty extension. So an empty extension is when you have a predicate or a property that nothing actually satisfies or nothing meets the conditions laid down in order to be counted as a member of that group of things or to be counted as having the relevant property. So for instance, consider the property of being a unicorn. The property of being a unicorn is an empty property in the sense that there are no unicorns in the world, and because unicorns don't exist, the property of being a unicorn has an empty extension. So to get a sort of sense of how this works, we're going to draw two different properties. One property is going to have an extension with things in it, and the other property is going to have an empty extension, just to show you that extensions don't necessarily have to have things in them. So first of all, I'm going to draw, here's the property of being yellow. Being purple. We're going to call that property P. Right, now here's the purple things. Some various shapes and blobs. Right, so the property of being purple does, in fact, have something that satisfies it. Here are some purple things, so we know that the extension for this property is not empty. But if I look at the property of being a unicorn, and I draw the extension for this property, the extension for that property is in fact empty. There's nothing that satisfies the relevant property. There are no unicorns in the universe. So the extension is empty. So this is what I mean by the extension for a property or a predicate can be empty. We can still talk about unicorns. We can still use the property being a unicorn in conversation and in language and indeed in argument, even though there is nothing in the world that actually satisfies that property. And that's going to become really important. Sometimes what we do when we are interpreting these properties that have empty extensions is we say that the extension of the property corresponds to the empty set. So the empty set is a technical notion inside set theory. You don't need to worry too much about what the empty set really is, but basically for our purposes, we can think of the empty set just as a set of things that has nothing in it. And whenever we are interested in a property that has an empty extension, what we say is that the extension of the property is the empty set, right? There's nothing that corresponds to that property. In set theory, we draw the empty set with a particular notation. And that's how we draw the empty set, like that. And sometimes you'll see this thing in some of your assignments and problem sets. All you really need to know, you don't need to know any set theory, all you really need to know for our purposes is that this thing is telling you that the extension of a particular property or predicate is empty. There's nothing that satisfies that predicate for the purposes of the question or the problem or the argument that you're actually assessing. Okay, so we've got the concept of an extension. An extension just corresponds to a set or a group of things that have a certain property. We've got the concept of an empty extension, and that's the case where an extension has nothing in it, where there's nothing that satisfies or possesses the relevant property, like the property of being a unicorn. And now what we're going to do is we're going to take this core notion of our semantics, this notion of an extension, and we're going to apply it to particular cases and then to the universal and the existential quantifiers. So first, let's just have a look at a couple of examples without the quantifiers, and then we'll have a look at more complex cases involving the quantifiers. So suppose that I have this property px, where x is yellow. Right? This notation, when I say px, x is yellow, is just a way of writing down the extension for the predicate and just specifying the set of things that the predicate applies to. So consider this property, the property of x is yellow, and suppose that A corresponds to Steve the lemon. So Steve is a particular lemon. He lives in my backyard. He's a good friend of mine. And that's what the lowercase letter a picks out. Now, I want to know whether this claim, PA, is true or false. Which is to say, is it true or false that Steve the lemon is yellow, right? Which is what this says. So in order to determine that, I look at the set of yellow things, and I look to see whether or not Steve the lemon is in fact in that set. And it turns out that Steve the lemon is in fact inside the set of yellow things, and so it follows that Steve the lemon is yellow, which is to say that this claim here is true when A picks out Steve the lemon. But suppose that I introduce a second name, and this second name, lowercase b, is Sally the strawberry. And now I wanted to know whether Sally the strawberry is yellow. So, this time I'm interested in the claim PB, where the claim PB is saying that Sally the strawberry is inside the set of yellow things. So I look to the set of yellow things and I see that in fact Sally the strawberry is not inside the set of yellow things. Rather, Sally the strawberry lives over here inside the set of red things. And she's a little bit unhappy because she's not a yellow thing. And yellow things are better than red things. So here we have an example where PB turns out to be false. So the truth value of this claim that Sally the strawberry is yellow is false because Sally the strawberry is not inside the set of yellow things, whereas the claim that Steve the lemon is yellow is true because Steve the lemon is in fact inside the set of yellow things. Once we've got an understanding of an extension, we can actually start to chain together conditions in order to be able to say multiple complex things at once. So let's have a look at how that's going to work. So let's consider the following two properties. First property, A, is the property of being a pineapple. Yep. That's the first property. The second property is the property of being tasty. And what we want to do is we want to have a look at a particular pineapple. In this case, we're going to talk about A, where A corresponds to Joseph the pineapple. And what we want to know is whether or not the following claim, AA and BA is true. So we're trying to work out whether it's the case that Joseph the pineapple is a pineapple, so he's in the set of pineapples. We haven't just given him a terribly inappropriate name, and he's also in the set of tasty things. So what we have to do now is we have to have a look at two different sets. First of all, we're going to have a look at the set of pineapples. So here's the set of pineapples. And we'll put a third one in, why not? And over here we have the set of tasty things. I'm going to put Sally the strawberry over in the set of tasty things. She's a bit happier now. I'm going to put Steve the lemon over in the set of tasty things. And of course, we're going to have Joseph the pineapple as well in the set of pineapples and in the set of tasty things. So what we can see here is we've got two sets. This might remind you of Venn diagrams, and in fact that's exactly what these are. These are very basic Venn diagrams, and Venn diagrams appear in set theory, and the sort of basic concepts of set theory underline the concept of an extension. For our purposes, though, we don't need to care too much about Venn diagrams or set theory. All we need to see is that we've got two different sets here, and these two different sets have different objects in them, but they partially overlap with one another. So if we have a look at the set of tasty things, we can see that there are three tasty things inside that set. We've got Sally the strawberry, we've got Steve the lemon, and we've got Joseph the pineapple. They're all inside the set of tasty things. And over here, we've got a set of pineapples. We've got Joseph the pineapple, and then we've got two other unnamed pineapples. And because we've got something that lies in the overlap, the region between the two sets, right, this region here, which I'm colouring in purple, we know that we've got at least one thing that is both a pineapple and tasty. Now, because we've also said that this thing is in fact Joseph, then we know that Joseph the pineapple is in fact tasty, which is to say that this claim here, AA and BA, is in fact true. So Joseph the pineapple is tasty. Okay, so that's the basic idea behind using these extensions. When we're trying to work through the extensions, what we actually do is we have slightly different truth conditions for each of the basic connectives that we had in propositional logic, and that the sort of truth conditions that we had in the truth tables then get reformed inside the concept of an extension inside monadic predicate logic. So just to give you a sort of basic idea of how this works, it's useful to have a look at each of the connectives and look at the kinds of diagrams that you might draw when you've got something that satisfies the connectives in question. So let's start with the one that we've already had a look at. So let's have a look at AA and BA. Right? So when this is true, what we're interested in is the truth of the conjunction. Is it the case that A is in the extension of A and lowercase a is in the extension of B? So if we're going to draw a picture of this, when it's true, what we end up with is something like this. We've got the set of A things, the set of B things, and right there in the middle is A, right? It lies at the intersection of those two sets, and that's what makes this true. What would make this claim false? Well, either A would be only in the left-hand circle here and not in the right-hand circle at all. There are sort of two ways to make this false. One of them is to put A inside that yellow shaded area. The other way is to put A only inside this yellow shaded area, in which case A would be in the set B but not in the set A. So there are sort of two ways to make the conjunction false. You can either have this side false, where A is not inside that big set A, or you can have this side false, where A is not inside the big set B. And that really corresponds to the truth table definition for the conjunction. Remember, the truth table definition for the conjunction is that the conjunction is only true when both sides are true. And here we've got the case where it's true, where both sides are true, and that's depicted with something falling in that region of intersection between these two sets. And you've got the two cases where it's, the sort of three cases where it's false, when A falls inside the set on the left-hand side and not in the set on the right-hand side, or it falls inside the set on the right-hand side, not inside the set on the left-hand side, or it in fact falls inside neither set. So if it's just completely outside this picture at all, then this claim is also false. And those correspond to those three rows in the truth table under which the conjunction was false. It's really just playing out exactly the same concept. Okay, next we're going to have a look at the disjunction. So here we've got, in this case, either lowercase a is in the extension of A, big A, or lowercase a is in the extension of big B, or both, right? So because there's the inclusive disjunction, you could also have the situation where lowercase a, in fact, falls inside the extension of both sets. So if we're going to draw a picture of this one, then we're going to draw a picture that looks something like this. We're going to take we're going to have two sets. This time we're going to have set A, and this time we're going to have set B. And we're going to put lowercase a somewhere inside these two sets in order to make this proposition true. In fact, if we put A anywhere inside the circles, we're going to end up making the disjunction true. If we put lowercase a here, inside the set A, well then this left-hand side of the disjunction is true. And remember the truth conditions for the disjunction. The disjunction is true when one side is true, when the other side is true, or when both are true. So if we put the A on this just in this left-hand side, we make that left-hand side of the disjunction true, then the disjunction gets to be true. If we put A in this right-hand side, then the right-hand side of this disjunction gets to be true because A is now inside the extension for B. And if we put A inside the intersection, we make it in both set A and set B, then both sides of the disjunction is true, which makes the disjunction itself true as well. The way to make the disjunction false would be to take A and put it right outside the entire set. So if A is right outside the entire set, then it's not in the set A, it's not in the set B, and so both sides of that disjunction are false, and that makes the entire sentence false. All right? And that just, again, recapitulates the basic idea behind the truth table for the disjunction. Remember, the truth table for this disjunction has it that the disjunction is false when both sides are false. And that's exactly what happens when we put lowercase a outside the extension of these two sets. All right, next, we're going to have a look at the conditional statement. So have a look at this one. We're going to have AA, arrow, BA. Okay. Now, what kind of picture can we draw to make this true? Oops. Put that back up. The kind of picture we can draw to make this true looks something like the following. So we start with the set A. So that's all of the things that have the property A. This might strike you as a little bit abstract, but you can put in whatever you want for these A's or B's as we're going. You could think of this as the property of being red, and this is the property being round, or something like that. We'll have a look at some more concrete examples in a moment. It doesn't really matter what these properties are. What matters more is the relationship between the predicates or the properties rather than the properties themselves. So here we've got the set of A things, so those are the things that have the property of being A, and here we've got the set of the things that have the property of being B. Now, if we want to make this proposition true, this conditional statement true, one thing we can do is we can put A into the center of this set. So what this is saying is that, sorry, I've done this around the wrong way. Got the order of the sets wrong. So the A set is the inner set and the B set is the outer set. What we're saying when we're saying that if A is in the big set A and A is in the big set B, what we're saying when we express that conditional statement is that if you put something inside the set A, then it has to be inside the set B. Remember, the conditional statement from propositional logic, if you've got the first thing, then you have to have the second thing. So if A is inside the first set, then it has to be inside the second set. And the best way to represent that is to nest one set inside the other. In fact, this is the sort of only sort of Venn diagram picture you can draw that will guarantee the truth of this conditional statement. Pretty much any other picture you draw is going to offer the possibility for a counterexample. So let's have a look at some other pictures. Suppose that I draw the relationship between A and B like this, which is what I initially had to start with. I put A as the outer ring and B as the inner ring. Well, then I could put A inside big A, but not inside big B. And so I would have the first thing, A is falling inside the extension of A, but it's not falling inside the extension of B, which is going to falsify the conditional. And in fact, this corresponds to that case in the truth table under which the conditional is false. So you've got the first thing, but you don't have the second thing. And because you've got the first thing and you don't have the second thing, the conditional gets falsified. So we keep that same truth table understanding of the connective for the conditional, and we just apply it to this sort of picture where we've got these different sets in operation. Of course, there are other options that we could have. So I could have this kind of picture, but I could do a couple of different things. One of the things is I could put A right outside of anything. Okay, so I could put A out here outside of the set A. And in so doing, I'm making it the case that the antecedent of this conditional, the thing on the left-hand side, is false because little a is not inside the set big A. And in that case, we just continue to adopt the same truth table understanding that we have for the conditional. So in that case, the conditional gets to be true, and it does not matter whether or not what's going on with the set B, which is just what we had in the conditional statement when we're looking at propositional logic. When the thing on the left-hand side of that conditional statement is false, then the conditional gets to be true regardless of what's going on with the thing on the right-hand side of the statement. And that might seem weird, and I think it starts to seem even weirder when you're dealing with these kinds of set theoretic situations, when you're looking at the relationships between properties, right? So for instance, if I say, if you're red, then you're round, and it turns out that you're not red at all, then the conditional statement is still true. And that might seem odd. How can the conditional statement, if you're red, then you're round, be true when you're not even red? And that sort of highlights one of the difficulties that we have with the conditional when we're translating from the English out into propositional logic and then again into this monadic predicate logic. What's core, though, is that we still capture the case which falsifies the conditional. So we can still do that. If we put A inside big A, but not inside big B, then we've got the first thing, we don't have the second thing. And so that conditional statement that if you have the property A, then you have the property B, turns out to be false. So if you consider the example, if you're red, then you're round, the falsifying situation would be a case when you are red, but you're not round, which is what roughly this picture with the lowercase a put inside the uppercase A set, but not inside the uppercase B set would look like. All right, so we've got one left to do. Well, actually, we've got two left to do. Let's do the hard one first, which is the biconditional. All right. Oops, I've written that in propositional logic. Just get rid of that. So here we're interested in this sort of dual conditional relationship. Now, one of the key things to think about with the biconditional that will help, I think, to make this sort of case understandable is to think of the biconditional as two different conditionals. So the biconditional is really the conjunction of a conditional going from A to B and a conditional going from B to A. So what we can do is we can draw a picture for each of those conditionals, which would make them true, and then we can try and combine those pictures in order to come up with something that will work for the biconditional. So let's start with making the top claim true. We can do that as we saw before by getting two sets. We put A as the inner set and we put B as the outer set, and that's going to ensure that whenever A or anything falls inside the set A, that it also falls inside the set B, which is going to make this top conditional true. So that's going to force that top conditional to be true. Now for the second conditional, which is going from B to A, we just reverse that relationship. And so we have it that the sort of small B set is inside the big A set, right? So that whenever we put A inside B, we can't help but put it into A as well. Now, if we want to combine these two pictures, right, what we have to do is we have to try and think of a way in which we can have A always falling inside both sets whenever you put it in one of the sets or the other, right? So if lowercase a is in the big set A, then it's going to be in the big set B, but also if you put it in the big set B, then you're also going to end up putting it in the big set A. And one way to do that is to do something like the following. Okay, first of all, we're going to get our set A, and then the next thing we're going to do is we're going to get our set B. I'm going to represent this by a dotted line. So what's happening here is that I'm actually getting these two sets to overlap completely, right? So you've got the A set and you've got the B set, and those two sets sort of contain all of the same things. So when this is the case, if I put A inside the A set, I can't help but put it inside the B set, which gets me that conditional. And if I put A inside the B set, I can't help but put it inside the A set, which gets me that conditional. And because both of those conditionals are true, I then end up with the biconditional being true as well. Okay? Of course, that's not the only way to make a biconditional true. The other way to make a biconditional true is to make both sides false, as we saw when we were dealing with the truth table for the biconditional. So one way to do this, if I try and make both of these conditionals if I make both sides of these conditionals false, one way to do that is to just take A and ensure that it's not inside the set A at all, and it's not inside the set B at all, which is to say that I just get the thing and I just lift it out of both sets and put it over here. So that's the other situation under which the biconditional is true. And keep in mind that when the thing on the left-hand side of these two conditionals is false, then both of these conditionals get to be true. So we are in another situation where we have both of these conditionals standing up, and that gets us the biconditional relationship. And of course, that's relying on this weird feature of the conditional, namely that it's true whenever the thing on the left-hand side is false, but that weird feature of the conditional is now being carried forward into the biconditional, which is kind of unsurprising because the biconditional itself combines these two conditional statements. Okay, so that gives you a basic idea for each of the two-place connectives that we had in propositional logic as to how they now apply inside monadic predicate logic. The last thing we need to deal with is the negation. So consider this sort of statement. It's not the case that A is inside the extension of P. Let's suppose that P is the property of being punctual, and that lowercase a corresponds to punctual Pete. And now we want to say it's not the case that punctual Pete is punctual. So punctual Pete, despite his name, is not actually inside the set of punctual things. We want to work out what it would make to make that claim true. So here's what would make that claim true. Here's the set of punctual things. And in here we've got lots of punctual people. We've got, I suppose, Gandalf, because Gandalf always arrives precisely when he means to, and he's never early or late, and so it follows that Gandalf is punctual. We also have Death probably in here, because I think Death is typically always punctual. You never end up with Death being late, and so on. So we've got a whole bunch of punctual things, and out here we've got Punctual Pete, who unfortunately has a terrible name because he's not inside the set of punctual things. And because he's not inside the set of punctual things, that makes this claim true. So that's what it would take to make the negation true. You just take the thing that is supposed to be inside the set that would make it true, and you just push it outside that set in order to get the negation true. If we wanted to make the negation false, we would just reintroduce Punctual Pete into the set of punctual things. So we'd have a good hard chat to Pete, and we try and get him to turn up on time. Okay, so that shows you how to take each of the basic connectives that we have in propositional logic and apply them inside monadic predicate logic using the concept of an extension that I introduced to you before. The concept of an extension just being a set or group or class of objects, each possessing a particular kind of property. Now what we need to do is we now need to take our universal and our existential quantifiers, and we need to try and understand them in the same terms using the concept of an extension. So let's have a look first at the universal quantifier. So here's what the universal quantifier says. We're going to have a look at this very simple quantified proposition. This very simple quantified proposition is just for all x, px, right? That's the basic proposition that we're interested in. What we're trying to work out is when that proposition is true or false. So first of all, let's have a sense of what px means. Let's suppose that p just is the property of being read. If I say for all x px, what I'm saying is that everything in the entire universe, remember that quantifier always wants to go big, everything in the entire universe is read. So what would it take to make that claim true? Well, here's a picture of what would make that claim true. So here's the set of read things, and it turns out that this is also the set of everything inside the entire universe. There's Mars, there's you, there's me, and there's all of the other things. There's not very many things in the universe. It turns out there's just 6 things. And this makes the universally quantified statement true. It makes the universally quantified statement true because everything is in fact inside the set of read things. Now, of course, if we're sort of being realistic here, if we're thinking about our universe, there are more than 6 things in our universe, and so this claim is not going to be true for our universe. And that's going to become important later on when we can, what does it mean when we can actually sort of come up with a situation like this, a sort of artificial situation in which a claim like the universal quantifier is true or false, even though that doesn't correspond to reality. We're going to get a sense of how to think of that later on. But for now, all that really matters is that you can see what it would take to make that universally quantified statement true when you've got that predicate immediately following it. Basically, everything in the entire universe has to be inside the set that corresponds, or the extension that corresponds to that predicate. All right, let's consider now the existential statement. The existential statement that we're interested in is ex px. So what that says is there is something inside the extension of the property p. Now what is p? Well, let's suppose that p is again the property of being read. Then what this means is that there exists something in the universe somewhere, we don't know what it is, that sits inside the extension of that predicate. So again, we can use exactly the same picture to represent this. Here's a picture of the set of read things, and inside the set of read things, there is at least one thing, namely the planet Mars. You are also in there because you're all read apparently on this model or this picture that I'm drawing here. But at least one thing is read, and that's enough to make the existential sentence that there is something that's read turn out to be true. Okay? So in summary, just to sort of summarize the way that these quantifiers work in their simple forms, the universal quantifier is true when everything that follows that the universal quantifier satisfies the relevant condition that the property lays down, and the existential quantifier is true when something in the universe satisfies the relevant condition that the property lays down. You can then think of what it would take to make the universal or the existential quantified statements false, right? So think about the universal quantifier. So consider this statement for all x px, right? Here's the set p. That's all of the things in the universe that satisfy the property p. Now, here's that outer box actually corresponds to all of the things that there are in the universe, and that universal quantifier always wants to go big, so it's ranging over all of the things. We put some things inside p, and then we put one thing outside of P. And what this does is it makes the universally quantified statement false. The universally quantified statement is false when there is something outside the extension of P. Because we've got one thing here, the triangle outside the extension of P, that's going to make the universally quantified statement false in this case. What about the existential statement? Well, let's have a look at one of those. EX, PX. Here's the entire universe. Here's the set P. And what we're saying is there is something inside the set P, or there is something that has the property P. Let's suppose that the property P is the property of being a Pegasus, which, if you don't know, is a mythical flying horse. In our world, there is nothing inside this set, and so this statement, there is something that has the property of being P, is in fact false in our universe. If you wanted to make it true, all you'd have to do is drop a Pegasus into that circle, but because there are no Pegasuses, that it follows that the statement is in fact false. You could easily do it with unicorns as well and say there is something that's a unicorn. That claim's also going to be false because there's nothing inside the set of unicorns when that set is taken in relation to the entire universe. Okay, so that gets us the simple quantified propositions, the universal and the existential. Now what we have to do is we have to think about more complex statements. So what we've got so far are basic propositions like PA and then the combination of those propositions with our propositional connectives, so things like and, or, if, then, and the biconditional. We've also dealt with simple quantified propositions, and that's where we don't have names following our basic propositions, but instead we have these universals and existentials following those basic propositions, so in front of those basic propositions, constraining them in certain ways, and that gives us the truth conditions for these simple quantified propositions. But now what we have to do is we have to look at the combination of these two things. So we're looking at the combination of the universal with a conditional statement, say. So it's something like for all, use something that's not yellow, for all x, if px, then qx, right? So we're looking at something that has both the universal statement in it, our basic predicates, and as well as that, a propositional connective like the arrow. We're going to have to look at things like there is something that's px and qx. So where we've got the existential statement and we've combined it with a conjunction to state a new kind of proposition, and so on for each of the combinatorial options that we have for our propositions and their connectives. We need to sort of think about what it would take to make each of those true or false. After that, we can then step back a little bit and come up with a general story about the truth conditions for some of these statements. Okay, let's have a look first at something fairly straightforward, namely the existential followed by a conjunction. So we've got there is something that has the property P and it has the property Q. That's what we're saying. So if we want to look to see what would make this true, let's give P and Q something concrete. Let's actually attribute some properties to them. And now let's look at the relationship between those properties that would be needed in order to make this proposition true. So let's suppose that P is the property of being red. Here we've got all of the red things. And let's suppose that Q is the property of being round, and here we've got all the round things. And now the proposition we're looking at is there is something that is both red and round, right? So EX, bracket, PX, and QX. That's the proposition we're looking at. Now what would make that proposition true? Well, to make that proposition true, we need to say that there is something inside the intersection of these two properties, inside the point where these two extensions for these properties overlap. So as long as there is at least one red round object, then the statement there is something that's red and round is going to turn out to be true, right? And that's all it's going to take to handle this kind of complex quantified proposition. Now notice I haven't named this thing. We haven't said, that this is Rudolph the round thing. We haven't done anything like that. We're just talking completely abstractly because we're dealing with variables at this point and not names. We're saying there is something that's red and round. We don't know what it is. We don't have a name for it. We don't even know where it is. But there is something because it lies in the intersection between these two extensions for the two properties. Now what would it take to make there is something that's both red and round false? Well, all we need to do is get rid of this round thing inside the intersection here and put it over here and make it black, right? So here I've gotten rid of the red round thing, and instead I've included a black round thing, and there is nothing inside the intersection between these two sets. There is no longer any red round things, and because of that, this existentially quantified sentence, there is something that's both red and round, turns out to be false, at least with respect to the picture that I'm drawing here. Okay, so next, let's consider a universally quantified statement. This is an important universally quantified statement to get a hold of. Here we have the universally quantified statement for all things. If they're P, then they're Q. Once again, what we're going to do is we're going to treat P and Q as particular properties. And in this case, we're going to continue to use that same idea of treating P as the property being red and Q as the property being round. And then we're going to have a look at the relationship between these two things that would make this universally quantified proposition true or false. Okay, so here's a picture that makes the universally quantified statement true. And what we're going to do is we're then going to try and alter the picture to make that universally quantified statement false. So what does this universally quantified statement say? Well, it says for all things, if they're red, then they're round. So what that means is that the set of red things is going to have to be a subset, or it's going to have to be located entirely within the set of round things. So here's a set of red things. Here's a set of round things. And what we can see from this picture is that the set of red things are all round because they're located inside the group of round objects. So that's going to make this statement true. In order to make this statement false, all we need to do is put one red thing into P that's not also round. Right? Because what this says is that for all things, if they're red, then they're round. So if there's one thing inside this set of red things that's not round, then it's no longer true that everything that's red is round. So what we can do is we can take one of these red things. What we're going to do is we're going to shave off the edges of this red thing that's round, and we're going to make it into a square. Okay, we also need to make it red. Hang on. Let's do that. Right, so now we've got a red thing that's not round, and because we've got a red thing that's not round, there is something in this set of red things that's not round, and so it follows that this statement up here, this universally quantified statement, is in fact false because there are red things that are not round. Okay, so next, what we're going to be dealing with is a biconditional statement. Now remember, the biconditional statement puts the relationship in two different directions. It's really equivalent to two conditional statements. So the biconditional statement that we're interested in here is for all x, px, biconditional qx. And what we're saying is that for all things, if they have the property P, then they have the property Q, and if they have the property Q, then they have the property P. So if we treat P as the property being red and Q as the property being round, then what we're saying is that for all things, if they're red, then they're round, and if they're round, then they're red. So it follows that there are no red non-round things, but it also follows that there are no round non-red things. The two sets completely overlap. So if we want to draw a picture of this case, here's what we've got. Here we've got the set of red things, and we've got the set of round things. And notice that those two sets completely overlap. There's nothing that's in one set that's not in the other set, and there's nothing in the other set that's not in the one set, right? The two sets have the same objects inside them, which is to say that P and Q have exactly the same extension. And so that is going to make this universal statement for all x, px, just in case qx, true. Because everything in here, in P, is also in Q, and vice versa. Now, if we want to try and make this statement false, there are a couple of different ways that we can do it. One way to do it is to put something in P that's not in Q, right? So what we could do is we could have a little blip in the extension for P like this. So we've got a little bump, and inside here we're going to put something that's red that's not round. Right, and that's going to make this statement false now because it's not the case that for all things, if they're red, then they're round, and if they're round, then they're red, because there's some red thing that's not round. And the other way to do it, of course, is to put another sort of bump over here in the extension for Q, and put something in here that is round but not red. Okay, so there we go. We've got a round thing that's not red, we've got a red thing that's not round, and either of those options would make this biconditional false. Because what's going to happen is that the two sides of the biconditional are going to have different truth values. You're going to have P being true, but Q being false, or Q being false and P being true. And that's enough to make that biconditional false, again, as we saw when we were dealing with the truth table. So we're just keeping those same truth conditions for the biconditional as we move into this more complex monadic predicate logic. Of course, the other way to make this universally quantified statement true is to just get rid of all of the objects that we have before us completely, right? So if I got white, yep. If I get this set of objects that are red and round, and I just get rid of everything from within this set, get rid of those things, get rid of this as well, get rid of this. It's all gone, okay? Get rid of all of those things and just empty this set out so that there's nothing in it. Well, then the universal quantified statement is also going to be true, right? If there are no red things and there are no round things, then you've got no way to make either of the conditionals, the sort of conditional going from left to right, false, or the conditional from right to left, false. You've got no way of making those two conditionals false, and if you've got no way of making those two conditionals false, then it follows that the biconditional is true. This is just that same peculiar behavior of the conditional carried forward over into the biconditional. All right, next let's consider the combination of the universal quantifier with a conjunction. So what we're saying in this situation is for all x, px and qx. So everything is in the extension of P and it's in the extension of Q. And now here, we've got to keep in mind that universal quantifier always wants to go big, and so what we're doing here is we're saying that everything in the entire universe has these two properties. So again, let's suppose that P means that P is red and that Q means that Q is round. Then what we're saying is that here's everything in the entire universe, and everything in the entire universe has the properties of being red and also the properties of being round. So what that means is that P and Q overlap each other entirely, because all of the red things are also round things, and P and Q overlap the entire universe as well. So everything in the universe has both of these properties together. Okay, and that's enough to make this for all x, px and qx true. If we want to falsify this claim, if we want to make this claim false, all it would take would be to get everything in the universe and make it the case that something is red without being round, or round without being red, or that there's something that's neither red nor round. So we could put in a black circle here, we could put in a red square here, and we could put in a yellow Steve the Lemon. And as soon as we put those three objects back into the universe, then it's no longer the case that everything in the universe is red and round, and so that universally quantified sentence for all things px and qx turns out to be false. All right, next let's have a look at the disjunctive statements. So this is a disjunction in combination with the universal quantifier. So this time we're saying for all x, px or qx. And we want to know under what conditions is this statement true or false. Now what we're doing is we're looking at the relationship between the universal quantifier and the disjunction here. And what we're saying is that everything in the universe either has the property P or it has the property Q. So if P is the property of being red and Q is the property of being round, then what we're saying is that everything is either red or round or both. So what's that going to look like? Well, here's a picture of what that would look like. Here we've got everything in the entire universe, and everything in the entire universe has one or other of these two properties. So we've either got red things, or we've got round things, or we've got red and round things, but we don't have anything that lacks one or other of these properties. So we don't, for instance, have a square black thing, which would be something that's neither red nor round. We don't have a yellow triangular thing, which again is something that's neither red nor round. Everything either has the property of being round or the property of being red, or both. You have nothing falling outside those two properties. And which is to say nothing falling outside the combination of those two properties. You might well have things that are red without being round or round without being red, but you don't have anything that lacks both of the properties. And again, that's just that truth table for the disjunction showing up again. The disjunction is false when both sides are false. So if I were to put something in the universe here that is neither red nor round, so if I put a black square up here inside the universe, then that's going to make both sides of that disjunction false, and that's going to make the disjunction false itself. But equally, just one side of the disjunction being true is enough to make the entire disjunction true. So if everything in the universe were red, or if everything in the universe were round, then that would be enough to make it the case that everything in the universe is either red or round. Okay, so hopefully you get the point by now. For each of these complex propositions, what we do is we take our understanding of the extension of the predicate, we take our understanding of the connective, the conditional or the conjunction or the biconditional or the disjunction, whatever you like, and then we take our understanding of the quantifier and we combine all of these things to produce a sort of combined set of conditions under which the proposition is true or false. When you've got an all and an and a property, you've got to put them all together and work out a kind of picture that will enable you to say whether the proposition is true or false. One of the nice things about monadic predicate logic is that you can in fact draw pictures that will help you to determine whether or not a proposition is true or false. And those pictures are going to be sort of toy pictures in the sense that you're not drawing pictures of the actual universe, so you're not sort of working out whether these propositions are actually true or false, but they can help you, those toy pictures, they can help you to work out what it would take for those propositions to be true or false. Okay, now the constructions that we've looked at so far, where you're using a universal in combination with, say, a conditional or an existential in combination with a conjunction, those are fairly ordinary or common constructions. There are a couple of odd constructions that can sort of be difficult to get your head around, so let's have a look at a couple of those. The first one is there exists something that's in the extension, such that if it's in the extension of P, then it's in the extension of Q. So here we'd have there is something such that if it's in the extension of P, then it's in the extension of Q, right? So here we've got an existential in combination with the arrow or the conditional. This is a sort of odd thing to say because on the one hand you're saying there is something, but then you're saying, but actually I don't really know much about it, and I want to say there is something such that if it has this kind of property, then it has that other kind of property. It is an odd thing to say. You might well find a reason to say this, say in a scientific situation where you say something like, look, there's a new kind of particle, we don't know if we know that the particle exists, and here's something else we know about it. We know that if it has one kind of property, then it has to have a certain other kind of property. So for instance, we know that quarks exist, and we know that if they have a certain kind of spin, then they've got to have a certain kind of charge or something like that. But we don't know if there is any quark that in fact has a spin or something like that, right? So you can imagine a situation where you've got a particle and you're a little bit unsure about what its properties are, and so you might well sort of want to say this if-then-ish thing about the relationship between the properties of that particle. What we're interested in is what would make this kind of statement true or what would make this kind of statement false. So let's get our property P, and we're going to get our property Q up. And what we need to make this thing true is that for there to be at least one thing such that if it has the property P, then it has the property Q. So what we're really interested in here is there being at least one thing such that if it has the property P, then it also has the property Q. So we're sort of looking at whether or not there's something that's lying in the intersection of these two sets. Okay? And if there is something lying in that intersection, so if there is something such that if it has one property, then it has to have the other property, which anything inside this intersection would have, then it follows that this existential statement is true. And if there's nothing that lies inside this intersection, which is to say there's nothing such that if it has P, then it also has to have Q, then the existential statement is going to be false. So if I were to get rid of this thing that lies in the middle of the P and the Q sets, or the extensions of these two properties, then that's going to be enough to make this existentially quantified statement in this situation. That's going to be a good start towards making this existentially quantified statement false, but what we also need to do is we need to say that there is something over here in P. And the reason we have to say that there is something over here in P is because if we want this existentially quantified statement to be false, we actually have to make this sort of relationship between the existential and the conditional yield the result that the proposition itself is false. If I were to make it such that there's nothing inside the extension P, then the left-hand side of this conditional here is always going to be false because there's nothing that has the property P. And if that left-hand side of that conditional is always false because nothing has the property P, then that conditional gets to be true because of that weird feature of the conditional where if the left-hand side is false, then the conditional itself has to be true. So if we want to make this conditional false, what we have to do is we have to put something in P that's also not in Q, because then we've got something that has this first property but doesn't have the second property. If we want to make it true, then we put something inside the extension of these two sets. Pretty much all of the work is going to be done with respect to P in making this proposition true or false. What's going on with Q is not as important. Okay, so that's the first sort of odd construction, and there's sort of range of ways of making this proposition false. I've shown you one way of making it false. Let's have a look now at a slightly different proposition. And this proposition is the existential quantifier in combination with a biconditional. And this is also a kind of odd thing to say. It's no weirder, I think, in some sense than saying an existential thing in combination with a conditional, but when you've got the biconditional, you're sort of doubling up on your weirdness because you're going to have the relationship moving from P to Q and back again. So let's draw a picture of what would make this claim false. So here we've got the existential, and we're saying there is something such that if it has P, then it has Q, and if it has Q, then it has to have P. So let's draw our pictures up again. We've got P. I'm going to put P on the same side as I put it on last time, actually. We've got P over here. We've got Q. Now we're going to try and make this proposition true. So one way to make it true is, in fact, to do exactly the same thing that we did last time, which is to say, put something inside the intersection between P and Q, because putting it inside the intersection doesn't just make it the case that if it has P, then it has to have Q. It also makes it the case that if it has Q, then it has to have P as well. So what you're going to do is you're going to get the biconditional relationship because you've got the conditional moving in both directions. If we want to make this proposition false, what we have to do is we have to put something in P that's not in Q, or we have to put something in Q that's not in P, right? If we've got something in Q that's not in P, we have to make it the case that everything that's inside P is not in Q and everything that's inside Q is not in P. So we have to, first of all, put something inside P and Q, and then we have to get rid of the thing that lies at the intersection between them. So this says there is something such that if it's in P, then it's in Q, and if it's in Q, then it's in P. If everything inside P fails to be inside Q, and everything inside Q fails to be inside P, then it's just not the case that there's something that sort of has this biconditional relationship between P and Q operating. Although we have to be a little bit careful here, because if we make both of these conditionals false, we might end up actually satisfying the truth conditions for the biconditional. So the biconditional here actually works a little bit differently to the conditional. When you've got the conditional statement, that getting it to be the case that there is something that has the first thing and doesn't have the second thing is enough to falsify the conditional. But in this situation, what we actually have is it being the case that there is something that has the first thing and not the second thing. So the biconditional from P to Q turns out to be false. But we also have it the case that everything that's in Q is not in P, so the biconditional from Q to P is also false. And because both of those conditionals are false, we're actually in this situation where we might end up making the biconditional true, because remember, the biconditional true is true when both sides fall together. And so when both of these conditionals are failing, you've actually got it to be the case potentially that both sides are, that the two things here are falling together. So what you want to try and do is make sure that you end up sort of making one side of this biconditional true and the other side false, so that you get that relationship you sort of get that case for the biconditional where the biconditional is actually false, namely when sort of it's standing on one side and falling on the other side, or vice versa. So the way to do that, when we're saying there is something such that if it's in P, then it's in Q, and if it's in Q, then it's not in P, then it's in P. What we do is we try and make one of the directions here false, but leave the other one to be potentially true. So one way to do that is to put something inside the intersection of Q and P. So what that does is it gets us the result that there is something, so that's not going to work. What we want to do is we want to get something such that if it has P, then it has Q, but it's not the case that if it has Q, then it has P. So we get it working only in one direction. And it's a little bit difficult to draw a picture of this particular situation because every time I try and put something in the intersection between these two sets, I'm going to end up making it the case that it sort of has one of the properties and it also has to have the other property. So I sort of make it the case that there's something that satisfies both sides of the biconditional. So what I can do is I can instead make it the case that that everything inside Q fails to be inside P. So that sort of gets me the biconditional working in one direction. And then I can imagine a situation, even if I can't draw it, in which even though that's the case, there's something inside P that fails to be inside Q as well. So actually, everything that's inside P fails to be inside Q. So what I can do is I can put lots of things inside P. And those things are all failing to be inside Q, so there isn't anything such that if it's in P, then it's in Q. So that first conditional is turning out to be false. But now what I want to do is I want to make the second conditional true, moving from the Q to P. And the way to do that is to get rid of everything inside Q, because that's going to make the antecedent of the thing in the sort of conditional going from Q to P. It's going to make this sort of side of the conditional false, which is going to make that conditional true. Okay, so just to sort of summarize what I was saying about the biconditional, to sort of make it a little bit clearer for you, with the biconditional, if you want to make the biconditional true, you just need to have something at the intersection between these two sets. If you want to make the biconditional false, you have to make it that one of these two conditional statements that feed into the biconditional is true and the other one is false, because that's going to get you the sort of differential truth value for the biconditional that you need in order to falsify the biconditional. And what I've done here to do that is I've made this top conditional false by saying that for all of the things that are in P, none of them are in Q, so that's going to make the direction from left to right false. But I've made the direction from right to left true by just emptying out the extension of Q and exploiting that feature of the conditional such that the conditional itself gets to be true when the thing on the right-hand side of that conditional is, in fact, false. Okay. So that gets us an account of a couple of these odd constructions. And what we can now see is that we've got a sort of proto-semantics for the language that we're dealing with. What we do is we combine our notion of an extension, which is this concept of a set that is associated with a predicate, or a property that is associated with a predicate. We take our propositional logic semantics for each of the connectives, and we combine those, and then we add them all together with our universal and our existential quantifiers in order to produce something that has the capacity to interpret each of the pieces inside our language. But remember, the focus of what we're trying to do, we're trying to come up with a way to test for validity and invalidity. And so what we need to do is we need to take this semantics that I've talked about so far and extend it to think about possibility, which is going to be the focus of the next lecture. Okay, thank you everybody, and I'll see you next time.